A very good morning to all of you, respected panel members and dear colleagues. Today, I, Dr. Gaurav Sharma from Atal Bihari Vajpayee Indian Institute of Information Technology and Management, would be giving my paper presentation on the topic on the effect of flow and degradation on hitting rate of mobile nanosensors in diffusive molecular communication systems. So during the course of the presentation, I would be discussing the following topics, and here are the outlines of those topics. The first, I would be discussing briefly about molecular communication. What is molecular communication and why molecular communication is being currently being so rigorously studied throughout the world. Second, I would be then put forwarding my contributions made by me during this paper, and I would also be highlighting my system model based on which the contributions have been made. After highlighting my system model, I would then be analyzing the performance analysis of the whole of the system model, and based on the performance analysis, I would also be discussing few numerical analysis results. And finally, after discussing the performance analysis and the numerical results, I would then be discussing the concluding remarks about my paper. Now, moving on. So, what is molecular communication? Molecular communication is the new communication paradigm which is very much prevalent in the nature. The primary objective of molecular communication is to observe, analyze, and interpret how the information is being transmitted from the transmitting nanomachine to the receiving nanomachine at the nanoscale level or the microscale level. Subsequently, this communication process, since in the macro scale is being obtained usually by the RF signals or the EM wave spectrum, whereas at the micro scale level, it's being observed through molecular communications. So that is why this communication process is being achieved between nanomachines. So these types of molecular communication analysis is being obtained in low energy constrained environments where the energy is a major constraint in whole of the system. Further, the molecular communication, which is very much prevalent in the nature, is being experienced through various chemical exchange between the transmitting nanomachine to the receiving nanomachine. Now moving on, why molecular communication is important? So first and the foremost, this is the communication between nanomachines. So how nanomachines communicate at the nanoscale level, which is different from the conventional EM wave spectrum. That is why we need molecular communication to be studied at the preliminary steps. Further, these types of communication scenarios would have low computational power requirement. Therefore, the power analysis of the molecular communication is also very important. So, particularly in nature, molecular communication is being experienced by chemical exchange. For example, the information exchange between molecules or unicellular organisms like bacteria, viruses is being achieved through molecular communication. Further, since the molecular communication is primarily based on the diffusion-based process, which is inherently has no diffraction losses. So this type of media or this type of communication is very much reliable. And this type of environments where, moreover, in those environments where radio communication usually fails, such as the pipelines, the underwater scenarios, the underground mines, in these types of scenarios, radio communication or the conventional EM spectrum based communication is not possible. So in these types of environment, molecular communication systems would come into picture. So, what is the motivation behind choosing molecular communication as a scenario in the current day-to-day life or the current research scenarios? So, the first and the foremost motivation is that the molecular communication finds its biological compatibility with the current healthcare systems, and they would subsequently, in the coming years, would be used as an installation of various devices in various healthcare fields. Since it's a new and the rapidly growing field where the reliable information transmission from the transmitting side to the receiving nanomachine is achieved, so this provides a higher rate of success compared to the conventional EM-based spectrum, where those types of spectrum is not providing any reliable information in particularly those environments where such as the pipelines, such as the underwater mines or underground mines and the underwater scenarios. So moving on, so Just like the conventional EM-based spectrum, wherein the modulation and the carrier-based phenomena is present, in molecular communication, the information is modulated either in the concentration or the type of molecule, and simultaneously in the particles number of the or the molecular particles number. Further, the information is nowadays being modulated, particularly in the molecular communication, in the release time or the time of release of the molecules. In addition to the modulation of the information, there are various channel transportation modes, which basically includes the diffusive based mechanism, the flow based mechanism, and the molecular motors, which is nothing but nowadays considered as biologically engineered bacteria, which are responsible for transmission of information from the transmitting side to the receiving side. So here are the few contributions made in the paper. The first and the foremost contribution which we did is that we calculated the average number of information molecules which are reaching the fusion center. Particularly, these types of molecules are being expressed as the type C molecules, which are nothing but the secondary biomarkers. And these types of molecule basically exhibit a log normal distribution, which is subsequently then utilized to obtain closed form expression for the average number of molecules when the molecules experience neither drift nor molecular degradation in the media. Subsequently, we also found the closed form expressions for the average number of molecules, for particularly when there is only drift in the media. And simultaneously, finally, and we incorporated the effect of both the flow-based mechanism and the molecular degradation simultaneously into the environment, and then calculated the how much average information or how much average number of molecules are being received at the fusion center in the environment. So based on these contributions are made based on the system, a particular system model. So this particular slide represents the system model of our paper. So here we consider the mobile nanosensors. These mobile nanosensors are being injected into the injection site, and these are nothing but the type A molecules. The mobile nanosensors on propagation throughout the blood vessels come in contact with the primary biomarkers. So these primary biomarkers are basically nothing but the protein molecules which are being released by the cancerous cells. And these cancerous cells, on reacting with the nanosensors or the mobile nanosensors, are converted into the secondary biomarkers. So the secondary biomarkers, which are nothing but the type C molecules, basically exhibits the log normal distribution, and these types of molecules are then received at the fusion center where the further processing of the detection of the cancer or the early detection of the cancer and various other information is being decoded. So this system model is based on certain assumption. The first and the foremost assumption is that the whole of the communication environment functions as a spatial and temporal component, with aqueous media experiencing no temperature and viscosity changes. So there's a uniformity in the temperature as well as the viscosity changes in the environment. And the second assumption is that the information molecules are identical and the transmission slot is large enough so that there is no intersymbol interference. Simultaneously, the third and the important assumption is that the transmission basically starts at x equals to 0, which is nothing but the origin point or the injection site where the mobile nanosensors are injected, and they simultaneously begin at time t equals to 0, with the fusion center acting as a fully absorbing receiver, which is only sensitive or which is only able to absorb type C molecules, which are nothing but the secondary biomarkers. So now moving on, basically based on these assumptions, we find out the probability density function of a type A molecule. So based on certain analysis, we found that the probability density function of type A molecules basically exhibits the particularly for a semi-infinite structure, basically exhibits a kind of a Gaussian behavior. And thus these type A molecules which react on reaction with primary biomarkers helps in obtaining the type C molecules, which are nothing but the secondary biomarkers, for which the type C molecules are basically exhibiting the log normal distribution. And these type C molecules, basically the density of the type C molecules is being shown in the slide particularly. by this expression. So moving on, we need to have a basic we need to calculate the basic distribution of the type C molecules. So utilizing the PDF of the type C molecules, we calculate the distribution of the type C molecules for a semi-infinite structure, because blood vessels is basically semi-infinite cylindrical structure into picture. And based on this performance analysis, we calculate the first and the foremost method is the basic. And the point to be noted here is that this type C molecule distribution is independent of both the drift velocity as well as the flow velocity as well as the molecular degradation. Now, in the second case, let us consider the molecular degradation. By incorporating the molecular degradation, which is nothing but a function of a particle or a molecular half lifetime. So this molecular degradation is incorporated into the basically the hitting distribution of the type C molecules, and based on this analysis, we come to an expression for the type C molecules wherein we can incorporate the effect of a molecular degradation. So this slide basically represents the hitting probability or the average number of molecules which are being received at the receiving site or the fusion center when the molecular degradation is present. Practically, molecular degradation is being observed in the current human body also. There is an enzyme called as the ACH enzyme, ACHE enzymes, which break down the information molecules, which are nothing but the ACH molecules. And this breaking down of the information molecules basically inhibits the propagation and the subsequent reception of the ACH enzyme, ACH molecules at the particular destination inside the human body. And this ACH molecules are basically responsible for the muscle movement throughout the whole of the scenario or throughout the response of the human body. So in addition to the molecular degradation, we also incorporated the flow velocity of the system, wherein the effect of the flow velocity is taken into picture. Particularly, we incorporated the degradation parameter, and we also added the flow velocity and subsequently calculated the average number of molecules which are hitting or being absorbed at the fusion center. And this expression is basically incorporates both the flow as well as the degradation, molecular degradation into the system. So based on the flow and the molecular degradation, the first numerical analysis comes into the picture. Here, the number of molecules here we basically plot the received molecules at the fusion center versus time. But here, the molecular degradation is varied, and in this case, there is no flow velocity present in the system. So the molecules only travel by drift scenario. As you can observe that with an increase, we have basically injected 1 lakh molecules, transmitted molecules, which are 1 lakh mobile nanosensors. On reaction with the primary biomarkers, certain number of molecules are being propagated as a type C molecules, and those type C molecules are basically responsible for the reception of at the fusion center. Since in this particular case, there is no flow velocity, so the reception is very less. So this type of reception where no flow velocity is present is significantly affects the overall performance analysis of the system. As we can see that with an increasing molecular degradation, the reception of the molecules significantly decreases, and with simultaneously with an increase in time also, there is a particular decay in the reception of the molecules at the fusion center. And subsequently, in the second scenario, we have now incorporated the flow velocity, but simultaneously we have reduced the molecular degradation to 0. That is, in the environment, there is no molecular degradation present. So simultaneously, we can see there is a significant increase in the reception of the molecules. Again, we have plotted the received number of molecules at the fusion center with respect to the time. So we can see that with an increase in the flow velocity, there is a simultaneous decrease in the reception of the molecules. This is basically due to the mechanism of collision between the molecules. Since the molecules are moving with a certain flow velocity, they will come in contact the with each other, and on impact with each other, their energy, or the activation energy, inherent activation energy would get reduced. So when they reach at the receiving side, they are not being able to absorb. They're not absorbed at the receiving side or at the fusion center. So in this case, basically, we have not considered the molecular degradation, but in practically, we have to incorporate both the flow velocity also, as well as the molecular degradation also. So without the molecular degradation, the actual analysis of the system is incomplete. So in the third case, basically, we have now taken the consideration, we have now simultaneously taken into consideration the molecular degradation also. So we can see from the analysis is that with an incorporation of molecular degradation and the flow velocity, there is a simultaneous gap or the simultaneous decay in the reception of the molecules. This is primarily because that when we introduce the molecular degradation, the actual amount of molecules when no molecular degradation was present is based simultaneously or significantly reduced because of the destruction of the molecules in the environment. So, but we can say that the flow velocity gives a basic added advantage in the reception of the molecules, since we have transfer. Since in the first case we are only able to for a purely diffusive environment, we are only able to achieve up to few hundreds of molecules reception at the fusion center. But when we introduced the flow velocities, the actual picture came into the consideration, and large amount of molecules are now being received at the receiver. So based on these numerical analysis and the performance, basically the performance analysis and the numerical results, we come to a few conclusions. So the first and the foremost concluding remark which I would like to put forward in front of all of you is that we obtained a detailed analysis of the firstly the effect of drift and molecular degradation on the reception of the average number of molecules at the fusion center. Simultaneously, we analytically calculated the closed form expressions for the average number of received molecules at the fusion center when molecules in first case when the molecules basically experience neither drift nor molecular degradation. So this in this case basically the closed form expression for a purely diffusive environment is being calculated. Second, we basically also calculated the closed form expressions for the second scenario where we calculated the expression for the molecular degradation, and then we finally introduced the effect of drift into that closed form expression for the average number of received molecules at the fusion center. So from all of these analysis and from all of the previous numerical results, we can say that average molecular reception at fusion center is less when neither drift nor molecular degradation is present in the environment. So it basically signifies that for a purely diffusive environment, the reception of the molecules is significantly low. And based on those reception of the molecules, even if we transmit a large set of molecules, we would only be able to achieve a very limited amount of molecules, which would certainly impact the overall performance of the system. So, but when we introduced the effect of a drift into the media, we can observe that with an increase in the drift, or with an increase in the drift, or with the introduction of the drift velocities or the flow velocities, the average molecular reception increases. But if we keep on increasing the drifts also or the flow velocities due to the collision effect of the molecules among each other, the overall performance of the system again decreases. So it is important to have a trade-off between all of these parameters. First we need to incorporate all the parameters, the drift velocities, the temperatures, the viscosity, the Reynolds numbers, and all of the diffusive environment case scenarios And then based on that, we can formulate a particular hypothesis at the receiver. And based on that receiver, we can make an estimation of a basic cancer or the basic need for the whole of the system. So basically, in the concluding remarks, I would like to say that the extension of this work can be to incorporate the effect of all the practical parameters, or more practical parameters, such as the size of the particle in terms of its Reynolds number, which is nothing but dependent in terms of its Reynolds numbers, and the temperature variations, the viscosity variations of whole of the environment. And in the receiving side, the receiver should be now considered as a basically as a partially absorbing receiver, such that few of the molecules after reception are being again injected into the whole of the media. So based on this, the following we can extend the current result or the current analysis to a more concrete extensions, where basically we can have a system with with the more practical parameters, and simultaneously we can increase or we can incorporate the hypothesis testing at the receiving side. And based on the receiving side hypothesis testing, we can estimate the detection and we can estimate the overall system performance, which would then be useful for the detection of cancers at the early stages. So all of this analysis is being looked up as a biomedical application, wherein we will incorporate basically our system into a kind of an early detection case scenarios or early cancer detection case scenarios. So with this, here are the few references wherein if you can, which basically utilizes flow-based mechanisms and various other important mechanisms for early detection, and particularly they use mobile nanosensors in blood vessels. So based on this, with this, I conclude my presentations. So thank you for your time and patience.